Okay, so our next speaker is Daan Crommelin from CWI in Amsterdam. And his title is here, Modeling of Unresolved Scales with Data-Inferred Stochastic Processes. Thanks.
Okay, thanks Andrew. So this is work that I've been doing with a whole bunch of people listed here. Jesse and Nick are grad students of mine at CWI. Some people in Delft from KNMI, the Institute of Meteorology in the Netherlands, and Eric was involved in a very early stage, Joseph Biella during a sabbatical visit. Okay, so the focus for this talk is the problem of parameterization in atmosphere-ocean science, and that is, roughly speaking, the problem of how you can include the effect of unresolved processes, subgrid scale processes on the resolved model variables. So it's a well-known problem for atmosphere and ocean modelers. One of the best known, and I should say most notorious examples is the problem of atmospheric convection, which I put up here, so you get a bit of a feeling for what this is about. Convection processes, so it's the process of moist air rising up. The moisture condensates, or can condensate if it gets above saturation level, clouds form. There's all kinds of complicated thermodynamics that can be involved there. And all this takes place on a fairly small scale. You have to think of scales smaller than 1 kilometer. Now by contrast, forecasting models, numerical weather prediction forecasting models, have grid scales on the order of say 10 to 40 kilometers. Global models anyway. And then of course for climate simulations, resolutions are coarser because they have to be run over much longer time spans. So there you can think of grid sizes, horizontal grids, mesh sizes of 100 kilometers and up. So obviously these models will not be able to resolve convection explicitly, but yet you need to include it because an atmosphere without convection is really very different from the atmosphere we know. So there's no way you can simulate the climate system reasonably well if you do not include this one way or another. Okay, so here's a sort of graphical depiction again of the skill problem. These are two sort of older and somewhat newer climate model, so you see a little bit of the sort of the mesh sizes that are involved here. This is the Hadley Center model. And here it is essentially the same thing. So this is from the Dutch buienradar. I guess only Peter Jan knows what that is about. So the rain radar that you can see over the Netherlands. So here's again sort of roughly, I mean, this figure is a couple of years old, so the sizes should maybe be shrunk a little bit, but this is there's a typical mesh size of a global model, one grid box. This would be a regional model, but then of course you see all this. So this is all rain, white and light blue for light rain, and there's some red there for heavy rain. So there's a lot happening there. There's a lot of dynamics taking place just within a single global model grid box. So how can we go about this? Right, so similar problems where the convection, atmospheric convection is surely the sort of the phenomenon that people concentrate most on when they think of these stochastic methods for parameterization. But of course, it also applies to other problems. One of them being, this is a topic that has not been worked on much so far when it comes to stochastic parameterization. It's ocean modeling. You see three figures of same flow fields modeled with an ocean model at different resolutions. I think this is 1 degree resolution here. It's, if I'm not mistaken, 1/12. So you see here there's all kinds of structure relating to the Gulf Stream that is not being resolved in these coarser scale models. So all the transport and mixing that's due to the turbulence that you see here at in the jet, right, somehow needs to be taken into account. Okay. Now, if we look at it at a sort of a little more idealized level, here's a sort of a simple two-dimensional equation for non-divergent flow. That you can see as a prototype or idealized model for atmosphere and ocean flow. And the model is a stream function psi and related to the vorticity q. They're related in this particular way. And for this, I assume that many of you are not into atmosphere ocean modeling, but rather molecular dynamics. So I thought I should put up some of these words here. So the velocity fields, right, just stream the velocities of the ocean flow or the wind are related to the stream function in this particular way, right? So this gives you a sort of, in a nutshell, geophysical flow dynamics that you can use to study these kinds of problems. So there's some terms.
The condition is the condition why you say non-divergent. What do you mean by non-divergent?
That's this condition here.
Satisfied.
Yeah. So there's this is flow. There's wind forcing. That's the F. There's the viscosity term in here. There's a Coriolis force, or approximately sort of the beta plane approximation of it, as you see right there. And of course, the sort of the cause of all problems in this respect is, of course, a nonlinear term, which just comes out of the advection term of the Navier-Stokes equation, and it looks it's often written in this particular form. This is the advection term from Navier-Stokes. Okay, so this, if you, yeah.
So this is, I mean, since I'm not into atmosphere science, so this is a model for 2D flow, I guess.
Yes, horizontal flow. Yeah, that's right. Yeah. So there's, you can think of it of two-dimensional ocean flow. So there's no vertical extent. There's wind blowing over it, forcing sort of the ocean to move in a certain direction. There's viscosity, and then there's the Coriolis force that causes all kinds of interesting
I have
phenomena.
a question. The equation by itself
Yes.
is exact and the phenomenology enters in the modeling, or also the equation is approximate?
It's the
Hydrodynamics, you know that the equation in principle is exact. Then to close the equation, you do approximation, right?
well, this both, I guess. So this is derived from can be derived from full Navier-Stokes through a whole series of assumptions, approximations, scalings, and so
It's
on.
already the mixing of the two. The starting point is always Navier.
Yeah.
The
That's right,
conservation law,
yeah.
but then you okay.
Yeah, but the problem I'll be talking about, and actually in the next slide, doesn't have to do with that. Of course, there's all kinds of error, if you will, that comes into these models that are due to these approximations and simplifications. But then on top of that, there's the problem that even if you assume that this is sort of the perfect and holy truth, then if you start coarse graining, there's essentially it's a classical problem in turbulence. You get these subgrid scale stresses that you have to account for somehow. Okay, so that's what I've tried to sort of summarize here. If you start coarse graining, you can think of it sort of in a kind of a large eddy simulation viewpoint as convolution with the spatial filter, for instance, Gaussian filter, which gives you a kind of coarse-grained vorticity field Q bar. And the equation for this coarse-grained field is almost the same, except for this little annoying term right there, which is the subgrid scale stress term, which cannot be expressed exactly in terms of the Q bar that you the coarse-grained Q, and it's essentially the difference between the nonlinear term applied to the coarse-grained quantities and the coarse-grained nonlinear term applied to the exact quantities. Okay, and the problem is that this subgrid scale stress term is space and time dependent. Okay, so this is something in principle that you cannot just approximate with a constant quantity. Okay, so how do you go about that? Well, the classical, sort of traditional, conventional way, at least in atmospheric ocean science, to do these kinds of things is by deterministic means. In this context, for this idealized problem, you can think of expressing B as a function of result scale field Q bar, for instance, by assuming some sort of form of turbulent viscosity in this particular way. Now, as an alternative, you can think of to approximate this subgrid scale stress term by a stochastic process that is dependent, however, on the Q bar. Right? That would be you want to condition it on the state of the resolved scale field if you model it as a stochastic process. Okay, so here are a few figures to make this more tangible. So this will be like a typical realization of this Q bar, this coarse-grained field. This will be this the stress term. And then of course the problem is that there's more than one realization for this B term, this subgrid scale stress term, possible for the same Q bar state, right? So that's of course the motivation to think of stochastic methods to represent this. So as I said, for every resolved scale state, there can be different realizations of B. It also means that if you start thinking of the distributions for this B term, if you look at a single spatial point, then the distribution for this B is going to be dependent on the value of Q bar at that same point. And of course, the fact that you can think of it stochastically is that it sort of reflects the uncertainty about whatever happens at the subgrid scales, because you don't model it, you don't know it. So this introduces uncertainty, and this is sort of the motivation to consider these problems from a sort of stochastic viewpoint. Okay, now in atmosphere ocean science, there's been a whole range of approaches that have been proposed to tackle this. A lot of it's actually relating to atmospheric convection. So there's sort of data-driven approaches, which is I guess the class that the ideas that I'm presenting here falls under. There's sort of systematic, I've dubbed it here semi-analytic sort of class of methods that Eric has also been involved in. There's ideas coming from statistical mechanics. People have been using cellular automata to model these processes. There's ideas coming from Ising model, Markov chain setups, and more. It's very diverse. Okay, so the idea that I've been working on is the following. So this is it in a nutshell. You can simulate in a way we're lucky in atmosphere ocean science that at least we do know. I mean, it is impossible to simulate all these processes in all detail at a global scale. But at least we know the equation, we know the physics, so we can simulate all the processes. So the idea is to simulate at high resolution. So simulate in this case, in terms of the equation I showed before, simulate this Q at high resolution. So you obtain sample paths for both Q bar and B. Then infer a stochastic process, a suitable stochastic process for this subgrid scale term B, conditions on this coarse-grained field Q bar, and then once that's done, as you go back to the coarse-grained equation, and then you simulate your Q bar with this B emulated, right? Rather than using the exact B, so you emulate it with this stochastic process, and that should be much faster and much more efficient than running the entire process. So that's.
Step one, you mean you run like a high-resolution regional model, because you can't simulate Q against the global.
Exactly. Yeah. So I probably have that on the next slide, or the one thereafter. That's right. So for all kinds of purposes, it's not possible to sort of do fine-grained simulations for the full domain that you're ultimately interested in. Sometimes you can. It's just very expensive. You do it once, you collect all the statistics, and then you can use it later on for much more extensive coarse-grained simulations. But for other purposes, you can think of concentrating on a sort of a limited area, using a limited area model to do the high-resolution simulations.
But then you need to think of boundary conditions or other external factors like the large scale.
Yeah. You need to think of. We haven't progressed to that stage yet, but you can think of sort of embedding it in a coarse-grained model. Yes, and in fact, it is. So you can simulate, but one of the things that I'm involved in right now is actually not use simulated values for these Q and B, but actually observations. And of course, you need the observation of good enough quality to be able to do that. But we do have a data set available for atmospheric convection that actually allows you to do this. So then there's no simulation involved at all.
You need to fit just from data.
Yes. Yeah. Yeah. This is from convection cloud tops and but it's data for atmospheric convection. It seems to be detailed enough to do this. Yeah. Okay. Well, so here's your point exactly, Dimitri. So it's typically too expensive to simulate at high resolution on a large domain. So you limit your domain to do this. And then, of course, the idea is that you infer a process for B locally in space, and then use replicas of or copies of this process that evolve independently from each other in your coarse-grained simulation. So you get this whole sort of network of these processes that you use in the coarse-grained simulation. Yes?
Do we assume that B doesn't have any memory?
Yes. Although, well, there's a way around that. Right? There's all kinds of limitation, and you can sort of stretch that, try to be more general. But ultimately, if you want to infer this from data, then sort of every generalization you need more data in order to be able to do this. So that's a drawback. Okay, so as I said, it's going to be sort of typically spatially localized processes. So I just focus on one sort of segment of the spatial domain. I look at whatever value of Q bar I have, and then the distribution for B, and that's sort of the basis for the stochastic process for B that I want to infer. And then once that's done, I just cover the world with copies of this process, as you see here, and that gives you a way to emulate this B all over the domain. Okay, so how's that done? As already asked about, yes, I assume it's a Markov process for B locally at every grid point. As already said, it's conditional, dependent on the resolved scale state Q bar at that same grid point, and then essentially all in quotes you need to do is evolve this B at every grid point by sampling from this conditional transition probability. So the given Q bar and B at the same grid point at a time point, you sample from a distribution to update the B, and then you do that for every grid point separately. And you can think of variations of that. You can add all kinds of conditions. For instance, you can say, well, let's also condition on the time derivative of Q bar at that same point. Or if you are convinced that sort of long-term memory effects are very important, then you can also say, well, I'm going to condition on B at an earlier time point as well. You can add many things, obviously, but then with every condition that you add here, right, there's more parameters to be inferred from the data. So you need more and more data to be able to do this. So the basic setup is like this. Okay, so it's a Markov process, but conditioned on this Q bar.
So the Markov process will not depend explicitly on spatial position.
No.
So
No. In this setup here.
So you then do this at every grid point, but then you can look at all of the data at all of the grid points to fit a single model.
What do you mean by
I know Q is varying across the grid points, but the Markov chain itself doesn't depend on which grid point you're at.
That's
so
right.
Therefore, all of the data collected at all of the different grid points can be combined together to infer the single model.
Yes.
Or B given Q.
Yeah, in principle, you can think of combining all the data if you have data available from all kinds of different locations. Yes. Yeah. So that's I know. In principle, it depends a little bit on the phenomenon. If you think of convection, I mean, it shouldn't really the physics and dynamics of atmospheric convection shouldn't really. Say in the tropics, it shouldn't matter whether you're somewhere over the equatorial Atlantic Ocean or somewhere over the Pacific. I mean, the physics of it, the underlying principle should be the same. So in that respect, it shouldn't depend on the exact geographical location. Of course, it can happen that some geographical location, the Q bar will, on average, take on different values than another location. But then, so
Model,
exactly, because it's conditioned in this particular way. Yeah, that's right. Okay, so practical implementation. What we've been doing mostly so far is make this practical by modeling these processes as Markov chains. So small states, discrete Markov chains. So that means that this bk can only take on a finite number of values. That has to be. Where typically B is a continuous quantity, so you need to discretize somehow. This can be done all kinds of ways. So clustering is one example that I'll show something from later on. The advantage of doing it in this way, in this discretized way, is that the estimation and the computation are very easy. Right? It's very straightforward. If you have to think about, for instance, inferring a diffusion process that is conditioned on some external variable, Q being Q bar in this case, that's complicated. It's very complicated. So Markov chain makes life easy in this respect. And the result of that is you get this kind of hybrid model set up where you have a set of ODEs for your Q bar coupled to a whole network of Markov chains for this unresolved process B.
With the Markov chain, you can often lose the structure a little bit. I mean, if you wrote down a continuous time model for Q, B given Q bar, and you fit the parameters in that, you might see something in it that's more interpretable than the Markov chain.
Well, so I'll show you a little example of that. So that we've been experimenting a little bit with modeling B as an Ornstein-Uhlig process with parameters that are dependent on the Q bar.
Okay.
Yeah. So that's not very strict. I mean, there's ways to make this, to do this without having to discretize. Okay, so these are some of the preliminary results that Eric and I started working on this using one of the Lorenz models, which gave interesting results, but I think this is maybe intuitively a little clearer to see what is going on, in particular for people with a molecular dynamics background. This is the Katchansik heat bath model, where you have the one distinguished particle coupled to a whole bunch of other particles which make up the heat bath. So it's the setup that was described in a paper by Andrew with a co-author a while ago. And this particular way, so there's the Q and the P. In this case, Q is just the position of the distinguished particle, not to be confused with vorticity, as I wrote it earlier on.
I didn't understand if you gave or not a justification for the fact that you can use a Markov modeling, Markov process modeling. I mean, I don't get if you justify that or just assume that.
I just assume, mostly, yes. Yeah, you can think of tests to verify this.
It must depend on the grid resolution and what amount of coarsening you're putting in, right? Like, yes.
Whether you can do this.
Because
I guess so, but it's not.
The grid is kind of analogous to, say, what Eric was talking about when he's reducing the state space by looking at particular.
Well, I think if you coarsen by a lot, then you can sort of go back to a deterministic representation by just assuming the mean value of all these unresolved processes. So again, in terms of atmospheric convection, if you take, you have these sort of convective elements, these thermals that rise up. If you take a huge domain, and you can say, well, on average, given this sort of large-scale atmospheric state, on average, maybe you'll see 100 or 1,000 of these convective elements in my domain. Then you're not going to deviate very far from it, so you can just assume it's the mean. The problem comes in if you go to smaller domains, where you have maybe 5, the mean will be 5 convective elements in one grid box, and then of course the fluctuations are going to matter a lot. So it's a bit difficult to pinpoint how this should relate to the grid size.
My question was because if that's your model, and that's your model, and then you can only check from its prediction how much it is good, that's very painful because I have no reason to trust, and you have to verify everything. If you justify the hypothesis, that you can expect some reliability, and that you can see more.
Yeah, it'd be nice. So, so one of the things I hope to get to at some point is to maybe not so much justify the Markovian nature of B, but rather to say, well, if you represent B in this particular way, then you know you're going to get a certain quality in terms of, say, the mean and the variance and maybe some other moments of the resolved scale variable. Because in the end, I'm not interested in B, I'm interested in Q.
I understand, but it's the curling the important point. You want the solution of this system to be meaningful.
Yes, exactly. So the question is, to what degree do you need to emulate this B in order to get a good reproduction of...
fine has to be,
yeah. Okay, so let me go to the... I'm looking at time, and I've been told...
You have 15 more.
15 more, okay. So the corresponding heat bath, so of course there's no sort of spatial extent in this model the way there is in the model that I wrote down before, but okay, let's ignore that for now. So there's a distinguished particle coupled to the heat bath, and you can rewrite it, do a little rewriting in this particular way. So the coupling with the heat bath in this particular setup comes only through this sort of average position of the heat bath particles. And so this R term and the residual term. So the idea is that if you follow this whole approach, you can try to mimic this or emulate this with the stochastic process. So what you see here is a scatter plot of there's 100 particles in heat bath. There's the Q, the position of the distinguished particle, and in the vertical there's this sort of mean position of the heat bath particles. So you see there's a lot of scatter around this. There's definitely correlation. So you do want to, if you want to represent this R in as a stochastic process, you do want to make it dependent on Q because of the clear correlation you see here. So the blue small dots, that's the scatter plot of the sort of full model, and then I discretize it by saying, well, R can now only take on one of these sort of pink, or is it magenta, I think the name is, values, and then I'm going to model the jumps with as a Markov chain. Okay. So there's only 4 possible states for R, and of course the transition probabilities are going to be dependent on the value of Q. So it's sort of done in interval wise for Q. So here it works pretty well. So this emulation of R with this conditioned Markov chain gives you these results. So on the top there's the distributions for Q and P in the full model. Here's Q and P in this reduced model, and this reduced model now consists of Q and P, so the momentum and the position of the distinguished particle coupled to this Markov chain setup, and of course the time step can be much larger because you don't have to resolve all the fast heat bath particles anymore. So there's a lot of sort of computational reduction here. And it does a good job, so these distributions are pretty well reproduced, and then here's the time correlations of Q and P, which are tracked pretty nicely with this reduced model.
The full model is with you've let n go to infinity and written down the SDE, or is it?
No, the full model is 100 heat bath particles. And then integrated with this numerical scheme that you worked out in the paper that I mentioned.
Okay, can you go back? Sorry, what was the form that you picked for?
This one?
Yes. Can you explain the motivation here?
So you were asking about the exact form of this, so the potential here, which is
I mean,
quadratic.
as Andrew mentioned, there's a limiting equation here.
Yes, yes. So that's
So which actually is not a Langevin. It's like there's one more variable you need to add in general.
I know in the limit of infinite heat bath particles. You can
Right.
you go to
So,
or something
but
that process.
here you seem to not use that information. Like, so I'm okay. You made a guess about the red term. Like, it
Yes.
may be so what was the motivation? I don't even I don't quite understand the notation. Maybe.
Well, to have, I mean, the motivation for doing this was to have a sort of very simple system to test these ideas out on, which is even simpler than the Renz 96 model.
And so it's really it's just it's n is the size,
Yes.
and r minus q is just you're relaxing q.
Yes, it's just
Like
rewriting. So
additional
this is the full model. This is this coupling with the heat bath particles in this particular way.
Okay. So now I see. Okay.
So it's only rewriting.
Rewriting.
I just want to isolate the way that Q and P are coupled to the heat bath.
Okay. So that's the motivation.
Just sort of casting it in a sort of
Okay.
explicit
Sorry.
form, if you will.
But there is a sort of limiting equation of R which you could write down and then compare your Markov chain with that limiting equation.
So it's an n to infinity limit.
Yeah. Presumably you're doing a good job of approximating that.
No, I haven't tried that. I know there's this limiting process, but of course, I guess one of the advantages of this approach is that you can do this. There's no need to rely on
The limit.
the limit. Yeah.
You see the way it's written. I mean, the scaling seems to be bizarre to take the limit and going to infinity.
Here, yeah. Well, I did it. It's true. Yeah. Okay, so once it's so this. No, let me skip this figure. It's not so interesting. So one thing we've been doing very recently is try to think of ways to sort of get beyond this Markov chain framework. So how do you is it possible to do this in a continuous fashion? So very recently I had one of my grad students try to work out to the way to infer an Ornstein-Uhlenbeck process with parameters that are Q dependent. So here you see there. So this is again a scatter plot, and there's the mean and standard deviations of this of the process. So that seems to work with the results that we got out of it. Right now, they're either they don't seem to be as good as with the Markov chain. Right? Of course, there's all kinds of assumptions. You're restricting the process in a particular way if you assume it to be Ornstein-Uhlenbeck, right? If there are any skewnesses, for instance, in this cloud of points, you cannot capture that with Ornstein-Uhlenbeck, but you can do that with this Markov chain setup. Anyway, so this is a very recent step. Okay, so let me go back within what is it, 7-8 minutes and a half to atmospheric flow. So here's again spatial scales that are covered by different kinds of models, global climate and weather prediction models at large scales, and then there's, for instance, large eddy simulation, which is used a lot for convection studies, which covers sort of the range from 10 meters up to maybe 100 kilometers nowadays. Okay, 2 quotes from old and new IPCC reports just to convince you that convection is an important problem. Let me not dwell on that too long. So again, what needs to be done for convection parameterization? In a GSM model column, there's sort of vertical transport induced by convection. So it's turbulent fluxes of heat and moisture that you need to parameterize somehow. Now you can model this with high resolution models with large eddy simulation. Right, that gives reasonable modeling of convection. That's done with models that have horizontal resolutions on the order of 50 meters. And of course, if you look at these turbulent fluxes, they depend on the resolved scale state, as I've mentioned before. So here's one example. So this is an LES simulation on a 25 by 25 kilometer domain. This is about shallow convection, which doesn't go up extremely high in the atmosphere. It's up to about 3.5 kilometers. So what you see here, when you look at the figure on the right, is at a particular level. I think it's 1,000 meters up in the atmosphere. Sort of the turbulent heat flux sort of across the entire domain, which is where it fluctuates, but you could reasonably approximate it with a constant value. But if you go to smaller domains, you get enormous fluctuations. So this is what you see here. You get these enormous bursts on smaller domains. So this is 1.6 by 1.6 kilometers. And that, of course, has everything to do with the fact that in the entire domain there are all these thermals, these sort of convection kernels that move around, and they start up and they die out, and they go through their life cycle. And on average, there's a certain amount of these kernels present. But if you go to smaller domains, depending on which sort of subdomain you're in, either you see nothing going on for a while, and then suddenly one thermal starts to sort of come into existence there, and you get these sort of bursts in the vertical turbulent transport, and that's what you see here, and these sort of large negative values, right? So you cannot approximate this with a constant value.
You're comparing simulation at different scales, but I guess if you take the blue data, for example, and you average over it so that you over the small grid size to get to the big one, should I agree with the red, or is saying that do you have a problem of resolution here?
In a way, so this sort of it's maybe a little counterintuitive, but here the problem comes in by sort of going to smaller domain sizes.
Yeah, but if I understand correctly, you're saying if I look at fluctuation in the small domain, right, I see there's nothing, and then I see burst.
Yes.
But in the other simulation, you don't have small domain. You're looking at bigger one.
Yes.
Right? So I could take the simulation in the small domain and average the turbulent heat flux over as many small boxes I need to reproduce one of the big boxes in the other simulation.
Yes.
And then of course I would average out some of the fluctuation, but it could still be that I get the wrong answer.
No, if you add up all these sort of small domains, then it's exactly, you get the large scale domain.
But then it's saying that the larger the simulation on the big box is actually
well, in this particular simulation, because it's a run in steady state, for this phenomenon, so it's about shallow convection, which so even on a 25 by 25 kilometer domain, at least under the circumstances at which this LES was run, right, you could approximate it with a mean value, but not if you go to smaller domains. So this is kind of a peculiarity, at least when it comes to shallow convection, that people, if you look at large domains, that's not where the problem is. The problem comes in when you start looking at higher resolutions. People want to do sort of simulations and predictions at increasing resolution, and then you enter something that people call it the gray zone. So on one side, with incredibly coarse resolutions, you can approximate this with sort of fixed or at least deterministic values. On the other side of the spectrum, there's the large eddy simulation, for instance, and there everything is deterministic as well. But somewhere in between, where you resolve part of the convection but not all of it, or maybe you have like 2, 3, 4 of these convection kernels in one model grid box. This is where you're stuck, and you have to do something else. And of course, so that's shallow convection. Go to deep convection, which is stretches up higher in the atmosphere and has larger spatial structure. There, even the model grid boxes in climate models have only a limited amount of such kernels in them. So there too, you will run into this problem, these huge fluctuations in vertical transport. Okay. So as I said, high resolution data comes from LES. The subgrid scale response in this case are turbulent fluxes for heat and moisture. So the vertical profiles, these are not scalar quantities, they're vertical profiles, and they're between them strongly correlated. The result skill states are those sort of in quotes Q. Now again, it's not a scalar quantity in one location, but there are also vertical profiles, and this time it's for wind velocities. There's temperature and humidity. So the amount of degrees of freedom is much higher than you have in, for instance, this heat map problem. Okay. So here's some examples from in the blue. So there's a lot of curves overlaid on each other. In blue, you see sort of the vertical profiles for the heat flux and the moisture flux. So this is the vertical coordinate in the atmosphere. So it takes all kinds of values, but that's kind of peculiar structure. It's not easy to capture with some orthogonal basis. So the way we discretize is by clusterings or simultaneous clustering. So that results in centroids that are these red profiles, and every red profile on the left sort of corresponds to a red profile on the right. So every centroid contains two profiles, one for the heat and one for the moisture. Okay. So and then the Markov chain jumps between these 10 pairs of profiles, and of course you can then look at the occupancy statistics. So what fraction of the total domain is in a particular flux state, as I've called it here. On left you see what the large eddy simulation gives you, and on the right you see what this Markov chain setup gives you, and it does a pretty good job at reproducing these occupation statistics for the various flux states.
So how did you get the clusters again? How did you do the clustering again? I missed it.
This K means clustering, which is combining both the heat and the moisture profiles together.
You did that clustering of the heating.
Yeah, so these heat and moisture profiles, so they come at a bunch of vertical levels. So in a way, so I think there are 80 vertical levels all in all. So if you combine that, then you do clustering in a 160 dimensional space, which is for clustering actually not that complicated. Okay, the chairman is rising, so. All right, so let me. I have a whole bunch more slides, but I'll skip most of them. One thing I do have to mention is that there's the matter of spatial correlation, right? Because what I've explained so far is that you model these unresolved processes locally dependent on the result skill set, and of course that means that you do get spatial correlation, right? If you look at the larger scale patterns for this unresolved process, you do get spatial correlation. It's inherited from the spatial correlation of X. Right, because there's the conditioning. So if X is correlated in space, then B sort of inherits part of that. But the question is whether that is enough. And I think, depending a little bit on the phenomenon, it will not always be enough. So we've thought about ways to sort of improve this spatial correlation, and one way to do that, very natural if you think of this whole Markov chain setup, is to add coupling to the neighborhoods of the point that you're interested in, right? Which is the sort of K bracket. So if you think on a lattice, right? There's sort of 8 neighboring points, if you want to define it that way, and then of course you can condition on that as well. And what you then get effectively is a probabilistic or stochastic cellular automaton, right? Where you make the transition rules, or there were probabilistic to begin with, but then you make them also conditional on or dependent on sort of the neighborhood states. Now it can be done. The only problem is that you need a lot of data because there's so many possibilities. If you have 4 or 5 possible states for this B at every grid point, then you have 8 neighbors. I mean, the amount of possibilities sort of grows out of control very quickly. So we did try to do that on an example of deep convection, which I probably do not have time to cover also. Now, rather than looking at these flux states, we stuck to a typology or classification in terms of shallow and deep and stratiform, so different cloud types. They're sort of physically a little more intuitive to think of. So you get these kinds of patterns. Let me just focus on one If you do this classification, so this is a 57 by 57 kilometers domain. So there's absence of clouds is white. There are different cloud types indicated by these different colors. So this is the kind of structure that you try to model. It evolves over time. Some of these structures grow and then they evaporate again, and there's all kinds of things happening. So we try to model it with this whole Markov chain setup on a lattice by doing this conditioning in various ways. Conditioning on the result skill state, as I mentioned before, and there's this conditioning on the neighborhood states in a somewhat ad hoc way, I have to admit, just because the amount of possibilities is just huge. But it does seem to improve things. So this is again the fractions of these different cloud types, right? The occupancy statistics that I showed before. On the upper left, this is what the large eddy simulation gives. On the upper right is the sort of the reproduction of these fractions if you use a Markov chain without any conditioning, not on neighbors, not on this resolved skill state, this large skill state, nothing at all. So you do get pretty much correct mean values, but the fluctuations around it are just absent, and it does not track this sort of long-term evolution, which has everything to do with the time evolution of this result skill state. So that's not captured in this sort of most simple setup right here. And then gradually, if you start adding more and more of these conditions right here, you do see improvements in terms of the time evolution of these mean states, and there's the sort of fluctuations that are difficult to capture, but it does help to add sort of this neighborhood coupling. So you get the fluctuations that are indicated by these dotted lines for standard deviations. They do improve if you try to capture more of this spatial structure in the representation of these unresolved processes. Okay, I think I should stop here. In fact, I was already at the last one. Okay, so a couple of things. Using these Markov chains, as I argued, makes for easy estimation and computation, but of course it's not. I mean, it's not strictly necessary to do it in this particular way. The conditioning on the result skill state helps a lot. That's really a crucial element here, and it does also help to get the right correlations in space and time. I already mentioned that the statistical inference for the stochastic cellular automaton setup is very difficult just because there's so many possibilities. And then there's work in progress on implementing shallow convection and deep convection in an atmosphere model and playing the same kind of game for ocean modeling. Okay.
Thank you.
That's it.
I suggest that Bob sets up and Dan takes questions while we do that. Questions for Dan.
So the way you do your conditioning is, I would say, rather ad hoc. Any meteorologist would probably say, well, if you try to do deep convection, or any sort in the atmosphere, coupling, not coupling in the spatial dimension is sort of unphysical. If something goes up, it goes down in the next grid point, or a few grid points. So have you tried looking at the do a long LES and try to let the LES determine what good conditioning would be. You could join PDFs and stuff like that, and just push it. Just push the supercomputer and let's do it.
Do I not have a compatible plug here?
Oh, this is.
They may be shorter.
Well, there are definitely ways to. So we've looked at
Somebody had Macintosh laptop
correlations and some information theoretic measures to try to infer from the data what sort of has the most predictive power. Yes. Yeah. But then when it comes to, for instance, looking at, I should probably also give them this. For instance, you're also referring to the spatial localization. Yeah, of course. I mean, you can include more and more data in your search. That's definitely possible. but then you gotta have it available first of all. I think a lot of, and the typical setup for parameterizations is this sort of, you do it column-wise, right? So that's
But we know that that's nonsense for convection, so clearly we should do better.
yes, but then so there's this, if you make it sensitive to sort of the larger scale state of the atmosphere, that helps in creating a kind of spatial structure that you want to see. Yeah.